Hi there and welcome. We're going to be covering section 4.4 today, the natural logarithmic function. And first up, we need to look at a graph. It's going to be the inverse of e to the x, so we would expect that it is a reflection about the y equal x line. So the definition of a natural logarithm of x is that given the graph of y equals e to the x, the reflection of that graph about the line y equal x is denoted by y equals the natural log of x. Notice also that e to the x crosses the point 0, 1, and that reflection is at 1, 0 for the natural log of x. So the definition of a natural log is for x greater than 0, if y equals the natural log of x, if and only if x equals e to the y. So that's your definition, how to go back and forth within that. Now this is algebra related, so if you want a good review of natural logs, I suggest you look in your college algebra text, and that would give you a good reminder of natural logs. If you need some review, just send me an email and I can get you connected with some of that material. So the properties of natural logarithm, remember this is just meant to be a quick review. The natural log of 1 equals 0, and equivalently we can see that on the graph 1, 0 for the natural log of x. The reason is because 0, 1 is on the graph of y equal e to the x, so equivalently e to the 0 is 1. In property 2, the natural log of e equals 1. Equivalently, e1 is on the graph of y equals natural log of x. Because the point 1e on the graph of y equals e to the x, equivalently e to the first is equal to e. Yeah, okay. Property 3, the natural log of e to the x is equal to x. This is an important one. You'll be using this fact over and over again. Equivalently, e to the x, comma x is on the graph of y equals natural log of x. Because x e to the x is on the graph of y equals e to the x. So it's just that reflection. Property 4, you'll use this one as well. E to the natural log of x is equal to x. It's a really happy one. When you see this one, you can just you get really excited. Equivalently, the point, the natural log of x, comma x, is on the graph of y equals e to the x because x natural log of x is on the graph of y equals natural log of x, and they're reflections of each other. So we have these properties written here where property 1, the point 1, 0 is on the graph of y equal natural log of x, just kind of restating because 0, 1's on the graph of y equal e to the x. We've said that a few times. Property 2, the natural log of x is defined only for positive values of x, and we saw that on the graph with that reflection. The natural log of x is negative for x between 0 and 1. And the natural log of x is positive for x greater than 1. So let's look at that. We can see here that in between x equal 1 and 0, notice we have that it is negative down through here. And then from 1 and on, it is positive up through here. Notice that there's no red line over there where x is negative. Those are undefined. And also note that the natural log of 0 doesn't exist either. It's an isotope here as well. And we could also note that the natural log of x was an increasing function and concave down all the way along its domain. So let's look at the exponential expressions. Let's look at an example. Just do some algebra with this. If we have e to the natural log of 3 minus 2 natural log of x, all of that in the exponent. Let's look at what happens when we apply our exponents. We could say, well, that with the negative belongs in the bottom. I know that e to the natural log of 3 is just a 3. E to the 2 natural log of x breaks apart into e squared and e times the natural log of x. And therefore I can write that crazy looking thing as just e over e squared x. Nice. Let's use some algebra to see how we can simplify and solve this equation for x. So let's write down our equation. We have e to the x quantity squared times e to the 2 minus 3x, and then that equals 4. So let's remove our parentheses and use our power rules that we have. We have e to the 2x because we multiplied exponents there. Then we'll combine expressions. We have two terms being multiplied with the same base, so we can add those exponents. And when we add those exponents, we get e to the 2 minus x equals 4. That's pretty cool. Let's take the natural log of both sides. And then once we do that, we can get that 2 minus x out of the exponent. We have 2 minus x equals natural log of 4. And then we'll do a little manipulation in order to get x equals 2 minus the natural log of 4 when we solve that. Cool. And that would be an exact answer. If you got that decimal approximation on your calculator or some sort of rounded number, that would be an approximation. Let's do another. We need to solve the equation 5 natural log 2x equals 8 for x. Let's write down that equation, and then let's divide both sides by 5 to get that natural log all by himself. Once I do that, we're going to rewrite this in exponential form. So I'll have 2x equals e to the 1.6. Divide both sides by 2, and our exact answer is e to the 1.6 over 2. If you push the buttons on the calculator, you'll get about 2.477, and that's your approximate. So looking at b raised to the x, and how does that relate to e to the kx, we can say that b to the x equals e to the kx, where k is the natural log of b. So we can rewrite something that's given with a different base in terms of e, and it's going to make our lives easier if we're able to do this. Now, some common logarithms are the base 10 logarithms. And log asks the question, how many powers of my base do I have? So log 10 of 100 asks the question, how many powers of 10 is 100? And that's 2. Log base 10 of 1,000 asks the question, how many powers of 10 is 1,000? And that would be 3. Log base 10 of 10,000 is, how many powers of 10 is 10,000? And that would be 4, because 10 to the 4th is 10,000. So just looking at that algebra-wise. Well, let's look at another example. We have the graph of f of x equals -1 plus the quantity x minus 1 squared times e to the x. And we are showing this in the figure below. We've graphed that. So let's find the coordinates of the maximum and minimum points. Now we know maximums and minimums occur at critical points. So we'll want to find the derivative and set that equal to 0. So here we say that at maximums and minimums, the graph will have a slope of 0. We know that. Therefore, we must determine at what values of x the first derivative is 0. Just finding the critical points. Let's write down our given function. And then we're going to take the derivative. So when we take the derivative of that -1, that guy's gone. But we have an x minus 1 squared, and then we have an e to the x. So we'll need to use that product rule. So the product rule tells me that I'm going to write down one of them. So I'll write down e to the x, take the derivative of x minus 1 quantity squared, plus write down the x minus 1 quantity squared, and then take the derivative of e to the x. Performing that, I get e to the x times 2 times the quantity x minus 1 plus, and then I get that x minus 1 quantity squared times e to the x. Now, since I want to set this equal to 0 and solve for x, instead of multiplying it out, what I'm going to try to do is factor. So I'm going to look and note that I have an e to the x in both terms. There are basically 2 terms here. I have one term, let me get my pen here. I have one term here, and I have one term here. Notice I have an e to the x in both, and I have an x minus 1 in both. So what I'm going to do is factor out that e to the x and that x minus 1. When I factor that out, what's left in this first term is just a 2. When I factor it out here, I'm going to have one of those x minus 1s left. I'll simplify this just to make it look a little better. Set it equal to 0, and then I'll get that while e to the x can't be 0, x is either equal to 1 or negative 1. All right, so now we've got another step to do. The slope of the function is 0 when x is 1 or when x is negative 1. Now by looking at the graph, we can see that the relative max will occur when x is negative 1 and that the relative min will occur at x equal to 1. That's really nice. Now all we need is just to determine those corresponding y coordinates. So I'll just plug in a 1 to my original function, and I'll plug in a negative 1 to my original function, do that computation, and I get that we have a relative maximum at negative 1, 0.472, and a relative minimum at x equal 1, y equal negative 1, and that's all we have for section, I believe this is 4.4. If you have any questions, be sure and let me know. Thank y'all and have a wonderful day.